Let's go back to a regression model, a classical regression model, where we are going to look at the different outputs, and specifically we're going to go back talking about this R square here, the adjusted R square, the F statistic, and the partial F statistic. Just let's take, for example, here in this window, we go back to one regression model. This one, let's say, this one for YY4, we consider that YY4, it can be, for example, the income as a function of XX. We can consider that it is age, and XX2, which can be considered as the education level. These are simulated data, therefore this is not true. This is just to understand what we do for a pedagogical purpose. Sorry. If we run this command only, I'm going to remove my place where I am. I'm going to put myself here. Therefore, let's run it. And we can see, we can ask for this summary of this object reg m1. We define this object reg m1. When we run it, we have this output, this interesting output, where we have a residual standard error, a multiple R squared, and an adjusted R squared, together with an F statistic, which is here with 2 and 47 degrees of freedom. We have already roughly detailed this. Just as a reminder, we have the R square here, which is based on this formula, which says that this idea of dispersion of the outputs of the YY4 in the code, the YIs in theory in a regression model where we assume that the Gauss-Markov assumptions are validated, are true. There's this idea of dispersion of the YIs, the total sum of squares. It can be shown that it can be decomposed into the variation of the dispersion of the predictions obtained by the model, yi hat, for the ones that are obtained by the model with the estimates here for the intercept, for the coefficient of xx, for the coefficient of xx2. That enables us to create those yi hat, yi bar, this is the mean of the yi's. Thus, this is this idea of dispersion, this idea of sum of squares, that means dispersion, how dispersed are the predictions, yi hat. And here we have the residual sum of squares, that means the sum of squares between of the differences, the sum of square of differences between the true yi's and the yi hats, the true yi's minus the predicted yi's. It means that corresponds to residuals, yi minus beta naught hat minus beta 1 hat x1 minus beta 2 hat x2. This is yi hat. Thus we have here a residual sum of squares. This formula can be easily shown if we do not estimate the intercept, the beta naught. And from this, we get the R square, which is defined by this formula or this formula, that means 1 minus the residual sum of squares divided by the total sum of squares. That means the portion of the total dispersion which can be due or which can be affected to the predictions that we have. That means due to the model that we defined. This dispersions of the predictions is at the numerator, and the predictions of the yi dispersion of the yi is at the denominator. That means that if the predictions are close to the yi's, the more the predictions are close to the yi's, the higher this r square. And the more these predictions are close to the mean of the y's, the closer to zero the r squared is. The problem with this formula, as we already said, comes from the fact that if we add covariates in a model, it is sure that the r square will increase. The more you have variables, the better the predictions are. The closer, I would say, the closer to the yi's the prediction are, and the higher the r square. That means that if we compare two models with different numbers of covariates, there is a high chance that the r square of the model with the highest number of covariates will be larger. And when we talk about r square, we talk about a tool that should enable us to select a model. We would like to have a tool which says, okay, if this tool is close to 1, the closer to 1 this tool is, the better the model is, I would like to say. But it is not the case for the r square, because if you have a lot of covariates, the more you have covariates, the higher chance you have that your r square is larger. And having a lot of variables in a model does not mean a good model, does not mean a model that explains very well the income, that explains very well the output. In this case, that would be the income. If you have 100 covariates, you will have 100 covariates that explain the income. You will have a higher r square, but that does not mean you will have a higher r square with 100 covariates than with 5 or 10 covariates. But that does not mean that the 100 covariates are important. Absolutely not. You will have a higher r square, but you will have this higher r square only due to the fact that if you insert covariates and covariates and covariates, at the end you will have a r square which is higher, but without improving the explanatory power, I would say, of the model. This is not because you add covariates that do not mean anything that you improve the model. If you insert covariates in a model that have no meaning, we will see that in R again after. Yes, you will increase your R square, but this covariate makes no sense. If you want to interpret your model after with this covariates which makes no sense, you won't have any result that is relevant. We will see that in R in some minutes. We can insert, for example, to explain the income. We can insert the height, let's say, of the individual. We could imagine that we have this, for example, here. There is a model which is YY4, the income as a function of XX, let's say the age, XX2, let's say the education level, and XX4, let's say it is the height of the individual. And let's run this model. And let's make its summary. Let's write a summary for it. That would be regm4, summary of this object, regm4. And we get this. Look at this here. I added something which makes no sense. The height of the individuals, x64. Before, I did not have this covariate inside my model. This first, the summary of regm1 is obtained here, and I have R square, which is 91%.35. And if I go to the summary of the object regm4, what I observe is that I have 91%.4. 91%.4 is larger than 91.35. Therefore, if you react saying, if your reaction is, okay, if I want to construct a model, I'm going to take the model with the highest R square, this is not good. That means in this situation that you are going to consider the height as an important variable here. You are going to consider that the height is an important variable because you are going to select the model with the R square, which is the highest. That means that this R squared with 91.4%. That is important if you want to correctly select a model, to define another quantity which is more susceptible to provide us a good model. If you want to compare models with the same number of covariates, okay, you can use the R square because you have the proportion of the variation of the full data set, which is due to the variation, the dispersion of the predictions. And you compare them with two sets of covariates that are different, and then you can select the model for which you have the highest R square. That can be done. That can be done in the case where you compare sets of covariates that have the same size, the same P. But if you don't have the same P, obviously it's really possible that the R square with the highest P will be the highest R square. Thus we have to define in this case at least the adjusted R square. This problem is a very big problem. The selection of the number of covariates is a very important problem in statistics. But okay, a first step to decide which model could be interesting is to refer to this quantity adjusted R square. And let's look at this formula for the adjusted R square. It is very close to the formula of the R square. 1 minus RSS that we find here divided by TSS that we find here. But we multiply both the numerator and the denominator by a quantity. The denominator we multiply by 1 divided by n minus 1. If you multiply TSS by 1 divided by n minus 1, in fact what you have is the classical estimator for the variance of the yi's, the variance of y. This is the estimator of that. And at the denominator, if you put RSS, which is like this, and you multiply it by 1 divided by n minus p minus 1, p is the number of covariates, what you get, we already saw that in the two-dimensional case, this is in fact a sum of epsilon I hat. This is a sum of residuals up to the square. And if you want to estimate the variance of the residuals, we already said, okay, when you only have one covariate, you should put here 1 divided by n minus 2. 2 is the number of parameters. 2 corresponds, in fact, to the intercept and the slope. And We can think about that like this. If we have 1 divided by n minus 2 times the sum of epsilon I hat squares, that corresponds in simple linear regression, that corresponds to an estimator of the variance of the residuals. If you want to have a good estimator of the variance of the residuals in multiple regressions, that means when you have p covariates, you have to multiply this RSS by 1 divided by n minus p minus 1. This is an estimator of the variance of the residuals in multiple regression. That means when you have more than one covariate, where you have p covariates. If you have one covariate, p equals 1 in this formula, p equals 1, and thus your numerator becomes 1 divided by n minus 1 minus 1. That means 1 divided by n minus 2 times RSS. Thus, in this case, we have here an estimator of the variance of the residuals. Variance of the residuals at the numerator, variance of the outputs at the denominator. But what can we see when we see this formula? What is more important, in fact? What is more important is that we can realize that in this quantity, if P is high, this denominator is small. This numerator becomes large, and thus the adjusted R square becomes lower with respect to a smaller value of P. That means that when you insert too many covariates in a model, there is a moment where your adjusted R square is going to decrease. This is not the case for the R square. This is not the case for the R square. And here we are going to compare the two adjusted R square that we got in the two models that we defined, where you have two covariates that are important. That means age and education level. We have for the adjusted R square 90.98%. And if we add this additional useless, I would say, covariate height of the individual, you have an adjusted R square which is 90.84%. This adjusted R square with this additional covariate is lower than the adjusted R square without this covariate without any interest. That means that according to the R square, we would select the second model. According to the adjusted R square, the highest adjusted R square, according to this one, we would select the first model. And indeed, in this case, the first model is really more interesting than the second model. Therefore, the adjusted R square, in this case, does his job. He says, okay, if you take the highest adjusted R square, you should select the best model. Here it is the case, because adding a covariate in this case, which makes no sense, the height is not interesting. That does not increase the explanatory power, that's not really increase the explanatory power of the model of the covariates that are inserted in the model. Because this adjusted R square, this is the formula for this adjusted R square, and we understand that with this formula, we can imagine a process to construct a model. A process where we say, okay, we're going to begin with one covariate, after we insert a second covariate, a third covariate, and so on. And we see how the adjusted R square evolves. It is going to increase, yes, if the covariates have an interest in the model, if these covariates in a way explain the output, you will have an adjusted R square that increases. But at a moment when you increase variable after variable, there will be a moment where you increase variables that not really make sense, or variables that in a way are already inserted in the model before. And in that case, you will see that your adjusted R-square will decrease. And therefore that will be a good tool that will be a tool, I would say, to select a model, a better tool, I would say, than the R-square, which always increases when you insert covariates. But anyway, we should be really cautious with that, because variable selection is a very important domain in statistics and data science. And here we only give one tool, but this tool is not, unfortunately, it's not the best tool. There are other techniques that enable the user to have better selection procedures that captures the model in a really better way. But that's beyond the scope of this presentation. Okay, we have this adjusted R-square, we have the R-square, and with that we can construct this formula of the F-stat, which is very close to the two previous ones, TSS minus RSS, but divided by P, the number of covariates, divided by the residual sum of squares, divided by N minus P minus 1, and the size of the sample minus P, the number of covariates, minus 1. This is distributed according to official distribution with 2 degrees of freedoms, P and N minus P minus 1. That enables us, as we already say, to see if a model is interesting or not. If including a full model, beta naught plus beta 1x1 plus beta 2x2, plus additional terms if needed, to insert if is it important to introduce this model with respect to not introducing this model? That means, thus, the full model have a real explanatory power. Does the full model have an explanatory power different from 0? The F-statistics is always given when you ask the summary of your objects, when you run multiple regression. Therefore, you have this F-statistic here in 2 cases. Here you have F-statistic as well. In the 2 objects that we defined, we see that we have a model which is clearly significant. That means that we have a value of the F-statistic is large, when the value of the F-statistic is large. We look at the p-value. We see that the p-value is very small in those cases. That means that the model in the 2 cases is important. That means that the model explains something. That means that there is an explanatory power of the model. It's better to try to explain the income with the covariates that are inserted here than doing nothing. It's better to insert age, education level to explain income. It is also better, according to the second F-stat, to insert age, education level, and height of the individuals. It's better to do that than nothing, even though inserting the height makes no sense. Okay, we use this quantity, and when the numerator is large, that means when the predictions, when the dispersion of the predictions is large with respect to the residuals, that means that this quantity is large, and when this quantity is large, that means that the model makes sense. The inserted model makes sense. This is the F-stat, but there is also the partial F-stat. And this partial F-stat is explained by this formula. It's another video where you have RSS naught minus RSS divided by RSS here, and here we have P1 and N here minus P minus 1. This is N here minus P, the number of covariates, minus 1. And we should apply this in this in the context here of our models. RSS naught is the reduced model, we say that, and RSS is the full model. That means that our objective is to say more precisely, if we add 1 or 2 or 3 covariates, is it important? Is it important to add 1 or 2 or 3 covariates? Is it important to add a subset of covariates in practice? Here, in this case, that corresponds to a statistics which addresses the question, is it important to add in your model P1 covariates? Is it important to do that? To answer that question, we are going to apply this ANOVA function here. Here we see in this ANOVA function, you are going to introduce regm1 first and regm4. Regm1 corresponds to the case where we have 2 covariates, x6 and x62, age and education level that have an explanatory power. Clearly, they explain something. They have something to do with the income. And regm4, this is the model where we introduced in YY4, in the income, we introduced age, education level, and height of the individual. That means x64 doesn't mean anything. And I'm going to run this function, ANOVA regm4, here. I'm running it. What do we observe? What do we observe here? We observe an output where we have model 1. This is the first model. We could name it the reduced model. It corresponds to RSS0. We are going to explain that more just after. And here, model 2. This is the full model. We could name it the full model. That will correspond to RSS here. And here we have P1 saying, is it interesting to add a subset of variables here? And here, what does that mean? This subset of variable, this is reduced to one variable. This is x64, the height of the individual. Therefore, the question, is it interesting to add one covariate in the model? P1 equals 1. In this case, we have residual sum of squares, classical residual sum of squares that are obtained from this model. Therefore, we compute beta naught hat, beta 1 hat, beta 2 hat. We next compute yi minus yi hat. For every point, we compute the sum of squares of that, and we divide that by n. No, we don't divide that by anything. We have this residual sum of squares, and we insert it. We insert it here. And we also have this residual sum of squares not with a 0 here that corresponds to the residuals but obtained with this model, with the reduced model. Therefore, here the residuals yi minus beta naught hat minus beta 1 hat times x6 minus beta 2 hat times x62. Minus the residuals coming from the age and the education level. And how do we interpret the results? We have both residuals sum of squares here that are denoted here. We have the first one with model 1, and the second one with model 2. And here with model 1, we have 2.945. And with model 2, we have a residual sum of squares which is smaller, 2.928. But what we can say next is that adding this variable is not interesting at all. Why? Because we look at that digit, 0.6081. This corresponds to a p-value, a p-value at the level 5% should be smaller than 5%. In the case it is smaller than 5%, we can say that adding this variable is important. In this case, it's not smaller than 5% at all. It is 60%. It's more than 60%. Therefore, in this case, that does not mean anything to add this variable x64, this 8 of the individual. That is what is said when I apply this partial f-test. And I could apply it with, for example, reg M5. In reg M5, we can see that in this case we only consider age as covariate. We don't consider education level and height. And we could compare this model with reg M4. Reg M4 considering the 3 covariates. In this case, if we run it, we have this. And in this case, we can see that the residual sum of squares are really high for model 1, which only considers age. We have 20.825. In the case of the model with 3 covariates, we obviously keep the same residual sum of squares, 2.928, and here a p-value which is really smaller in this case than 5%. Therefore, this model, that the p-value here is almost 0. We thus can say that with respect to a model that only contains age, it is really interesting for the explanatory power to insert the 2 additional covariates, education level and height. Obviously, it is only education level that is important, and we can see it by running this regression, this partial f-test. Therefore, here we compare the reg M5, therefore only 1 covariate, with reg M1. Reg M1 considers 2 covariates, therefore in this case P1 equals 1. In the previous case, P1 was 2. In the previous case, we had 1 covariate. In the reduced model, we had 1 covariate here with respect to 3 covariates in the full model. The full model had 3 covariates and the reduced model had 1 covariate. Therefore, P1 was 2. Here, when we consider comparing a reduced model, which is reg M5, that means we only consider 1 covariate, and reg M4, and reg M1, only here this object considers 2 covariates. That means in this case that P1 equals 1. We only add 1 covariate, education level in this case. Thus, I'm running this partial f-test in this situation. If I do that, what do I obtain? I obtain a model with P1 equals 1, which is also really important. Adding this covariate, which is education level, with respect to only 1 covariate age, is really important because we have a p-value which is almost 0. That means that the reduced model, it's important to increase the reduced model to get the full model, the named full model in this case. That is for this partial f-test. The question is it interesting to add information coming from another variable? And we could also see that in the opposite direction. We could go from a full model to a reduced model. And we could say, okay, for example, the other questions could be, is it useful to have this covariate in my model? Wouldn't it be more interesting to remove that covariate? And we could say, for example, okay, in this case, x64, that means the height, is the height necessary? That is the same question, in fact. Is it important to increase the size of the model by adding a subset of covariates? Or is a subset of covariates really interesting in my model? Is in fact the same question, but seen in the two opposite directions. In one direction, we say, okay, is it important to add covariates to get the full model? Or is it really important to have this subset of variate? Wouldn't it be better to get to take only the reduced model? Is in fact more or less the same question. And these two questions are solved with this partial F test. If we add a subset of variables, and if the F test does not reject the null hypothesis, that means that we do not find any proof, any reason to statistically add this subset of covariates. If the null hypothesis is rejected, in this case, that means that we find statistically significant reasons to add this subset of covariates to the model, these P1 covariates to the model. In the case that we want to see if a group of covariate if it's worth inserting a subset of covariates. If the null hypothesis is not rejected, that means that we don't find any reason to add or to this, we don't find any statistically significant reason to consider that it's worth inserting this subset of covariates. That means in a way that statistically we don't find any reasons. That means that we are allowed in some sense to remove these covariates from the model. But if the test is rejected, if we have a rejection in this case, that means that yes, this subset of covariates, it's worth keeping this subset, these P1 covariates in the model. That is the whole interesting philosophy of this partial F test. And now I'm going to close this presentation with a remark concerning the polynomial regression. Indeed, in a classical regression, you could imagine that you add some covariates up to the square, up to the power 3, up to the power 4. You could transform your equation y equals beta naught plus beta 1x1 plus beta 2x2 plus beta 3x3 and so on. You can add some terms of the type beta 4x1 to the power 2 plus beta 5x1 to the power 3 and so on. As we have seen, it's possible to insert interactions, but it's also possible to describe y as a polynomial. We could say, for example, that in my model, there is an interest to introduce age, xx squared here. It's interesting maybe to insert age up to the power 2. And we could insert in the formula then income as a function of age, of education level, and of age up to the square. Let's look at what we have in this case, summary of this object reg M6. In this case, we have this summary, and what do we see? We see here the classical results. We have a formula that involves these three covariates, but one of the covariates is the age up to the square, but it can be considered as a covariate in a way, as a new covariate. And we see here an estimate for the intercept for xx, for xx2, but not for xx up to the square. Okay, this model is still significant, okay, but that's not the point here. I don't see any coefficient. I say beta 4 times this x up to the power 2, and I don't find here the estimate for the coefficient of what should be xx2. Yes, because in fact automatically the LM function in R does not consider it when it's not significant, when it's not important to add this variable in the model. It is immediately removed by R. If you want to insert, if you want to absolutely insert this x up to the square, this x up to the square in the model, you have to define another variable. You should say, for example, xx5, another covariable, is a row. You could write something like that. xx5, in fact, would be xx up to the power 2. In this case, you can insert xx5 inside a formula here as an argument for this LM function. Another simple way to achieve that is to write this formula inside, therefore yy4 as a function of xx plus xx2 plus y. Here you see y parenthesis xx2 up to the square, and you close the parenthesis here. If you run this function here, and if you want to get the summary of this regm6, this new regm6, you will get here a coefficient. You can see here, you will get a coefficient for xx2. This is the coefficient for xx up to the power 2, not xx2, xx to the power 2. We have something here, and we see here that we have a p-value for that, which is absolutely nothing. This p-value is really high, meaning, no, the p-value is not absolutely nothing. The p-value is very high, meaning that the impact of this x to the power 2 is absolutely nothing. Obviously, the model is significant. It brings something, but it is not due to xx to the power 2. xx to the power 2 does not mean anything. And we could run this through a partial f-test. We compare here regm1, which is the regression with the formula xx plus xx2, and regm6, this regression, this polynomial regression with xx, xx2, and xx2 and xx up to the power 2. And in this case, we see here that we have very similar residual sum of squares, but in fact, that means that we don't have at all to insert this square of a covariable, because here we see that we have a p-value. We have the same here and here. The p-value is very high here. That means that we don't have to insert this power of the h. There's also the partial f-test could be used here as well to see if it's important to add powers of the different covariables. Powers are powers of the different covariables that are involved in my model. Power 2, power 3. Are they interesting or not? We could insert that in the partial f-test, and the partial f-test gives an answer for that. And it's the same as well for interaction. To add an interaction, this is the same as adding a new covariate. To insert x1 times x2, this is as if you were inserting a new variable, let's say x3. Therefore, in this case, the partial f-test can also be used to see if adding an interaction is interesting or not. This partial f-test can be really useful in a lot of situations.